All right, for the next few minutes, we're going to go on an incredible journey, an invisible one. We're going to follow a single photo from the exact moment you hit send all the way to its arrival just seconds later on the other side of the planet. You might think it's simple, but trust me, the story of how it gets there is amazing.
I mean, it really does feel like magic, doesn't it? You tap a button and boom, it's there. But what's actually going on under the hood is this incredibly high-speed, brilliantly organized sprint across a global network. So how does that journey really work? So here's our game plan. We're going to break this whole journey down into 6 key parts. First, we'll see how your message gets sliced up into digital postcards. Then we'll check out what's actually written on them. We'll follow their crazy path on the internet's highways, understand the physical language they speak, see how they're checked for mistakes, and finally, discover how they're locked down to keep your stuff secret.
Okay, first things first, the breakup. You see, you can't just send a massive file across the internet in one giant piece. Think about it like trying to mail a giant wall mural. You can't just roll it up and stick it in a mailbox. You have to cut it into smaller, manageable pieces first. Yep, just like that mural, your photo or your email or whatever it is you're sending, it's chopped up into thousands, sometimes even more, of these tiny little chunks. It's really the only way to send something so big through the crowded networks of the internet. Each little piece gets packaged up to travel all on its own. And each of these little chunks has a name. It's called a data packet. And the postcard analogy is perfect. Each packet is like a little digital postcard that contains a tiny piece of your original message and is addressed to be sent on its own individual adventure. So if every single packet is a postcard, what exactly is written on it? How does it know where to go? Let's take a closer look at the anatomy of a packet and see what's in its travel kit. And every single one of these packets is built like a tiny digital envelope. It's got 3 absolutely crucial sections that contain all the instructions it needs for its entire trip, from who sent it to exactly where it's going. This slide lays it out perfectly. First, you've got the header. That's your address label. It's got the IP addresses for the sender and the receiver, and a super important sequence number so we can put things back in order later. Then you have the payload. That's the good stuff, the actual slice of your photo. And finally, there's the trailer, which acts like a quality seal. It's got data to check if the postcard got smudged or damaged along the way. All right, so our thousands of little digital postcards are addressed, they're sealed, and they're ready to go. Now, for the journey itself. They are all released onto the vast and frankly chaotic highway of the internet. This whole process is called packet switching, and it's kind of wild. Each packet is sent out totally on its own. Routers, which are basically the traffic cops of the internet, look at each packet's header and shout, "Okay, you, go this way, you go that way," finding the most efficient route at that exact split second. This means they all take different paths, and yep, they arrive completely out of order. The computer on the other end then uses those little sequence numbers in the header to piece the whole thing back together correctly. And this right here really shows you why the internet works the way it does. Packet switching is like our public highway system. It's flexible, it's efficient, and everybody shares the road. The old alternative, called circuit switching, is like renting a private, dedicated road just for you. Sure, it's reliable, but it's also incredibly expensive and wasteful. And that's why the internet relies on the beautiful chaos of packet switching. Okay, but here's a super important detail, a really common misconception actually. We talk about these packets like they're solid blocks of data flying around. But if you could zoom all the way in on the actual wire, what you'd see is just a single stream of individual bits, ones and zeros, flowing one by one. The packet is just the logical wrapper our devices use to make sense of that stream. So, if it's all just ones and zeros, how do those individual bits actually move? Let's zoom in even further and get down to the physics to see how data speaks the language of the wires. So for that long-haul journey your photo takes across the internet, its data travels using serial transmission. That's 1 bit at a time down a single line. It's super reliable over huge distances. The other way is parallel transmission, which sends a bunch of bits all at once over multiple wires. It's way faster, but it only really works for super short distances, like between the different parts inside your computer. And the flow of that data isn't always the same either. Sometimes it's Simplex, a one-way street, like your computer sending a job to a printer. Then there's Half-Duplex. Think of a walkie-talkie where you have to take turns talking. But your internet connection, that's the good stuff. Full-Duplex, a true two-way highway where data is flowing in both directions at the exact same time. Okay, our packets have been broken up, they've been addressed, they've been sent on their chaotic journey, and now they're streaming bit by bit,
But hang on, what happens if some of those bits get flipped or corrupted along the way?
I mean, seriously, with billions of bits flying around every single second, errors are absolutely going to happen. It's just a fact of life. So how on earth does the system make sure that the message that arrives is the exact same one that was sent?
Well, the answer is this really clever little system called the Automatic Repeat Request Protocol, or ARQ. Here's how it works. The sender sends a packet and starts a stopwatch. The receiver gets it and checks for any errors. If it's perfect, it sends back a little ACK for acknowledgement, basically saying, "Got it, thanks." If it's messed up, it sends back a knock, telling the sender to send it again. And if the sender's stopwatch runs out with no reply, it just assumes the packet got lost and sends it again automatically. It's simple, but it's an incredibly robust system.
All right, we are almost at the end of our journey. Our data has arrived, it's correct, it's been reassembled. But there is one final, and I mean absolutely vital step. How do we make sure that even if somebody intercepted our packets on their journey, they couldn't actually read them? And this, of course, is where encryption comes in. It's essentially the art of taking your normal, readable data, what we call plain text, and using a special digital key to scramble it into unreadable gibberish, which we call ciphertext. Without the matching key to unlock it, that data is completely meaningless.
Now, there are two main flavors of this. You've got Symmetric, which uses one single secret key to both lock and unlock the data. It's fast, but it's risky. I mean, how do you securely share that secret key in the first place? And that's why the internet relies mostly on asymmetric encryption. This is the really cool one. It uses two keys, a public key that you can give to anyone to lock data for you, and a private key that only you have to unlock it.
And as you can see from a tip like this, the level of technical detail that makes all of this work is just immense. Every single one of these values has to be precise. For instance, in networking, we talk about kibibytes. That's 1024 bytes, not just kilobytes. That's the level of precision that's required at every single step of the way to make your data's journey even possible.
So, and this is the absolute key takeaway here, encryption does not prevent spies from intercepting your data packets. No, its purpose is to make sure that if they do steal your data, all they get is scrambled, useless noise. The secret itself remains safe. Which leaves us with this final crucial thought. Anyone in the world can use your public key to send you a secret message, but only your private key can unlock and read it. That makes your private key the master key to your entire digital world, the one thing that guards your digital identity. So the real question is, how much do you value the thing that protects it?